So welcome back to the lecture, and I have one question here on the chat. Can we see the final signal flow graph again for the integration filter? The screen was showing the nodes while it was being built. Yes, of course you can. I will just show you that right now. I also apologize. This is during the term, I think I will get used to it, but it is incredibly tiring what I have to do in front of here, because what I do is I control a laptop and all of the tools while also controlling what goes over the live stream, while also making a model of what the students now know and think, while also there are 2 or 3 more steps. I can maintain this kind of concentration barely for 45 minutes, and not always. And frankly, when I leave here and sit in the train to go back west, I just slump in the seat and go. But that's just the bad part of it. The good part of it is this is really tremendous fun. So now I've talked a lot, and I hope that Aramatos, nice name, has now seen enough of the graph. I have changed it a little bit because, of course, I intend to continue now with doing nice things with the graph. So what do I intend to do? My plan was still to kind of get this here built with integrators. And the integrators which I have would be the GMC filters, which we have done in the first part of the lecture. And now in the first part, what I showed you was something that can create loops like this. So on the signal flow graph tool, I have now taken this loop and replicated it. And now you see that I have such a loop where I have a node 1 and a node 2. So if this here could be my I2 from before, and this here could be my V2 from before, then this is quite easy to do, except for one thing. An integrator that I have, the horizontal path which I have in my signal flow graph, it cannot just contain an S. It also needs to contain what did I want to say? It also needs to contain a capacitor C. So right now, if this should be a current and a voltage, 1 over S is completely the wrong term. So I have to take this node here and scale it. So what I have to do is divide by C, such that it is, okay, now I have used the scale path functionality of my signal flow graph tool. But of course, if I want this loop still to be the same, if I want to divide the path going into V2 by a C, then of course I also have to divide the path going out here. I have to multiply it with a C. This is what just now happened, such that the loop is still the same loop. And then I have another integrator here. And this other integrator also has a 1 over S here. And this 1 over S, now I rather do it a little bit farther. This 1 over S here could also be a 1 over SC. Now to be on the safe side, I call this C2. And this here I would call C1. Otherwise we will end up in trouble. C2, this was the same C. Here I call it C1. But this is 1 over S times C1. So here again, I would have the situation where I have a current node and a voltage node. Any questions so far? not. Now, how can I possibly go from the voltage node to the current node? If I want the lower signal flow graph to have the same structure as the upper signal flow graph, then of course I have to put something here which has the form of a transconductance. So voltage times transconductance is a current. So what I need here is a GM. Let's just call it GM1. What I'm now doing will not be exactly the same graph as in the lecture notes, but just bear with me. And then, finally, I need to close the feedback loop from here to here. This feedback loop originally had the gain minus omega p squared, but now it should have the gain minus omega p squared times C1 times C2, such that the loop is still the same. Now let's make this a little bit flatter, such that it is nicer. Okay, and that one. And then, of course, I have the input branch. The input branch used to be k omega p squared. And now here it should be k omega p squared times C1 times C2. And if I have that, then in principle, I should be able to get exactly the same transfer function I got before. Okay, now it is a reasonably nice graph. But now you wonder, maybe what has now happened? Because the thing I would actually like to have here, that would be a conductance, isn't it? So this here I would like to be a GM. And just like this here, it doesn't really look very much like a transconductance, but if you think about the units, here I have a capacitance time and angular frequency divided by something without the unit. So indeed the unit of this is Siemens, farad times radian per second. So this is a transconductance. Also, that one here is a transconductance, which you have at the top. Is it? Yeah?
I don't know if I've missed it, but now we've introduced GM1 in the loop.
Mm-hmm.
So the loop is now the same as originally.
It is not the same as originally, you mean?
Yeah, now it's a GM1 in the loop.
Yes. So this GM1 here now should have a different value. So I take this here, generate the Mason, such that we can go over to our calculator. So this is now my transfer function, isn't it? I call this T equals this. So T point simplify. And now you see that I have a GM1 in it. And if I make this GM1 here 1 Siemens, then, underscore. So what is then defined? It did it like this, cool. Now you see that you have the correct one. So while it may not make a lot of sense to make this exactly 1 Siemens, it may be the wrong value, because 1 Siemens is a very high value. What this here now actually means is, if I go back to the signal flow graph here, that you kind of introduced for yourself an additional degree of freedom. So, of course, this has to be 1 Siemens if you have it in this loop. But maybe this here is also a value you don't like. Maybe this is a value which is very awkward to you, which you cannot use properly. So then you can now trade off between the 2 values here and this value here at the input also. So for example, if this should not be 1 Siemens but 1 millisiemens, then nothing bad happens if you make this 1,000 times as large and this also 1,000 times as large, which may anyway be a very good idea, because what you have here right now is very low numbers. So if these are picofarad, these are very small numbers, maybe too small. So suddenly you have a higher degree of freedom. Maybe this I'm not going to save, but I could do it right now. Right now you have the GM here, which is very high, and then you say, this I2, this is now far too large. Yeah? It will give a value that is far too large. So I scale it, and I want just to only be it divided by 1,000, and without changing anything else. So now you see how you should change all the others if this value I2 would be too large for you. I revert that. And by going through the signal flow graph, you could now figure out which node, which level, which voltage, which current you would basically like to have at the correct level. So this, for example, I could make much smaller if I want. I think that would be the proper thing here. So now I have, other way around. So now I have managed to do something that should give me a very small, a much smaller proportion of the GM1. So I have now gone from 1 Siemens to 1 millisiemens. But now maybe I don't like it that this current here is so high. So I can also say I want to maintain the status quo from before, and I also want to make this current smaller by a factor of 1,000. Now it is okay again, and now you see the thing I said before, that now this has to be 1,000 times larger, and this also has to be 1,000 times larger. And like this, if you don't like it, that GM1 should be exactly 1, then you can change it as I showed you here. So writing a 1 here would actually have been the nice thing. If I write 1 here, then everything is okay. But then the units are not okay, and this is why I decided to just write down GM1. So let me go to the notes, to the lecture notes. Just check whether the guys on the internet see the same. They do. It does work. So going to the lecture notes here, which you have. This is now exactly what I did here in this part. I have to zoom a little bit out, otherwise I don't find it. So this is the way I argued in this part of the lecture notes. It's just that in this part of the lecture notes I didn't only give you a low-pass filter, but with the same way of thinking you could now go and also do a band-pass filter or a high-pass filter, or even a filter with a generic numerator. So by going here and not only having a forward path after it's the GM4 here, you also have this additional path here. By doing that, you are now able to build a filter with any numerator just by thinking about different ways of doing forward paths in the Mason gain rule. Yeah. But this is it already. That's everything. So if you have understood this and you have an integrator, then you are in principle able to build any filter you want, any filter, yes. Just by saying, oh, this is my filter transfer function, I convert to integrators. I do the basic structure of the integrator filter, and then I reshuffle the paths until I see something which corresponds to a driving point signal flow graph that looks the same as my circuits would look. And then you have your filter. And most of the GMC filters, so transconductance C filters that you will find, were originally derived by thinking about signal flow, even if the people who built it didn't think about it exactly in that way. But that's the point, you make integrator loops, period. Does anyone have questions about this before I go to a different kind of integrators? Yes, please?
Just to recapitulate, the GMs we put in just because having a GM of 1 is not practical? Like
Yes, a GM of 1 Siemens is not practicable. Yes, that was the question. Because if later we will look at this in the next in the lecture after the signal flow graph break. I will show you how to calculate how much power a transconductor needs. But for me, as an experienced microelectronics engineer, if I hear you want a GM of 1 Siemens, that would mean that if you have 1 volt, which is reasonable on an IC, the output is 1 ampere. 1 ampere? Are you crazy? I have built hearing aids where the total power consumption of everything is 1 milliampere, and you want 1 ampere, or a gaga? Yes? No, we're not going to do that. So 1 is totally not an option. 1 micro is an option, yeah. 10 micro is an option. 1 milli is already very high for me, yes. So, but that's not the point. I mean, that's an implementation question later. The point here is that if you think about it in these graphs, and if you have understood what it means to scale a node variable, that you can go and say, I want V1. Presently, if I calculate it, I will get voltages of 10 volts, and my maximum voltage is 1 volt. I go there, I say, at 1/10 of that, please. Yeah? And then you still have the same Mason rule, the same transfer functions. Then you have in your hands a tool which permits you to really design a circuit. Okay? That's it, with all the constraints. But let's not the constraint get into our way right now, because to understand what value of a transconductor is reasonable, you first have to have thought about how to build a transconductor, and that's definitely something for next week, not for this week. More questions? I also check online. It is very silent. So let's think about how to do a different kind of integrator. And of course, all of you who have seen integrators ever before have probably seen this kind of integrator here. So that would be an operational amplifier, an integrator with an operational amplifier. And already somehow you can smell that this is also an integrator loop, because that here is the standard integrator with a resistor and a capacitor in the feedback. That here is also a standard integrator, but because it has also a resistor in the feedback, it is a loss integrator instead of a lossless integrator. You somehow have a feed-forward path, and you have 2 feedback paths with resistors. And the only problem, the main difference to the circuit before you have is that this here is now an additional circuit. So why do we need an additional circuit? And the reason that we need that is that with an operational amplifier, it is not possible to build a positive integrator. You can only ever build inverting integrators. So 1 over SC is not possible. It is minus 1 over SC which is possible. And if you have two of them and then the feedback, it will have the incorrect sign. You need the negative sign in the loop such that in the end you have the positive sign in the denominator. So there you go. But to show you how this can be analyzed in an easy way, of course you could now go and then do the full signal flow graph, driving point signal flow graph of everything. I allow you to do that if you want to do that, but oh my boy, this is going to be complicated. It has lots of nodes and lots of loops, and I don't think you will see a lot. So maybe here it would be a good idea to use an analytical method. And analytical method means that you go and take parts out of the circuit and say, I have a sub part, it looks like this, and now let me analyze that sub part. And this sub part here would have some nodes here, one input node V1, one input node V2, then I have an intermediate node V3 here, and an output node V4. And the only node that I have in this circuit here that does not already have a voltage source connected, it would be this node here. So here I have a magic source, but this magic source I will not always draw. And this here is another simple driving point signal flow graph. This time I will not put it into the tool. I will take the next one into the tool, but not this one. For this one I have the nodes here, V3 and V4. And then from the V3, oh, that was the wrong number. So that is V3, I3. I apologize. I3, V3. Yeah. So here I have this Z3, this driving point impedance, which is 1 over the driving point admittance. And as always in these driving point signal flow graphs, if you do not remember it or know it, practice a bit more, watch the videos again. But in short, what you have between voltages and currents, you always have, as the branches, you would have the admittance of the component that connects them. So for this branch, you have the admittance of this component. For this branch, you have the admittance of this component. And for this branch, you would have the gain of this component, the amplifier. And the only exception is the driving point admittance, where in the driving point admittance, you will have the sum of all components that are connected, all passive components which are connected to this node. Like this, you can really quickly draw a signal flow graph which will let you analyze the circuit. And I have done this analysis, but for ideal op-amps. So in a field like this, it does not presently interest me very much what happens if an op-amp is not ideal. So I just say, okay, that would be the actual solution of the signal flow graph. I could always insert that if I wanted later. But more interesting is if it is a very good op-amp, what happens. And then you will, of course, get the very well-known solution from one of the voltages to the output. It will be minus the forward admittance divided by the feedback admittance. So this is minus Y1 divided by Y3. And from the other input, it is minus Y2 divided by Y3. So the total output, if both inputs are active, because this is a linear circuit, isn't it? So if you have the transfer function from the input 1 to the output and the transfer function from the input 2 to the output, then if both inputs are active, then the output is the weighted sum, and the weights are the transfer function. So you get the input 1 times the transfer function 1 plus the input 2 times the transfer function 2. So what we can now do is we can, with this circuit, do the same as before. We can add things, and our adder is a Y1 or a Y2 here. And we can also see to it that it integrates. So if Y3 is just a capacitor, then I have an integrator here. So I have exactly the same as before. If Y3 is a capacitor, I have 1 over SC. And if Y1 and Y2 are just resistors, I have their conductance there just as I had the GM1, GM2, GM3, GM4 before. So this is exactly the same way I can do signal flow graphs if I want. With one exception, I do not have control over the sign. This is always negative. But this now means that if I have the circuit here in general form, and I have understood this, I can now go for this tau Thomas backward. Now I jumped to the wrong page. Yeah. Again, I can now go to the tau Thomas backward and say, okay, knowing that it is much simpler, isn't it? So I can now read this circuit much better if I understand what an op-amp with feedback is doing. So I can get away with only looking at these nodes here and only the voltages. So nothing else. So I am now able to draw a signal flow graph which contains only those voltage nodes with that knowledge what the circuit is doing. So I make a new one, save it as tau Thomas backward. By the way, the tau Thomas backward is called after two people whose last names were Tau and Thomas. So there you go, it doesn't mean anything else. And this has 4 nodes. So this is the V1. Then I have the V2. V2. Then I have the V3. And I have the V4. So these are my 4 nodes. And now I can go through the circuit here and check what happens between the nodes. This here is the simple one, isn't it? It has 2 resistors, a G5 and a G6. Now let's make it even simpler. Let me call this G5 and this is also G5. So let's make it the same resistor. Now according to the formula I just saw below, this is minus G5 by G5 is -1. So the only thing that circuit is doing is amplify the voltage by -1. So I jump over to my graph and insert here the -1. Then I take the second last and this one and say what happens if I go from here to here. Now my forward conductance is G2 and the feedback conductance is SC2 in Laplace notation. So therefore the path I can draw into here is simply G2 divided by S times C2. But, now comes the but, not positive, because all of the gains or all of the transfer functions which I do with the op-amps are negative. Next, from V1 to V2, I actually have now 2 ways to go. So if it is this source which is driven, I go through here, from V1 to V2. And this goes through G3. So in the forward path I have G3, and in the feedback path I have the parallel connection of those 2 devices as the admittance. So from the input to this node, I would have minus, what was it, G3 divided by, and this is S times C1 plus G1. Put it a bit here. It is G4, thanks. Then we have, yeah, where was the G1? Do I have a G1? Oh, yes, it's in the feedback. Thanks. That's exactly the feedback. That's the next one we have to do. That would be what happens if the output source is driven, and I want to know what happens in that direction. It is again the same type of circuit, so minus forward conductance divided by feedback conductance. So then I go from here to here, and maybe make this a little bit flatter. And then here I have the same feedback conductance, so let me copy paste. Same feedback conductance, copy paste, and then here it is now the G1 in the forward path. Good. So this is then the full signal flow graph of this circuit. Very simplified, because now, of course, you do not have a, I just check something else. Because now, of course, you do not have more loops that are necessary. I have kind of included one of the loops here already in this signal flow graph. So I said, I take the G4 as a feedback conductance. So I put it into the driving point signal flow graph as a driving point impedance or driving point admittance. What I could also have done very easily is say, oh no, let me now perceive the far end of the G4 as an additional input, which happens to be V2. And then I can make a loop. That would also work, but it would be kind of ugly, because in this case it would give a self loop from the node V2 to itself, but still I could also make this something where you can see two loops. However, whatever rocks your bucket, as they say, however you like it, do it as you like it. But this is now it, and I can calculate the transfer function. And let me do it like this, such that the people online can also see it. I make another path here. I have to briefly label it with a 1, because if there is a single non-labeled path on the graph, you will not be able to calculate Mason. Because then it says, of course, hey, I don't know all of the branch weights. How can I evaluate it? Yes. So I put the 1 there. I generate Mason here. And then I can copy this and just paste it into that path. Okay? And now you can see from the result that this is basically a second-order filter. It is not a very nice result. If you want the really nice result, then you can go to the to our Python workbook here, paste everything. Now I call this the new T. So T point simplify. And now if I want this to look nicer, I think I did not import the Hansby tools yet here. Will you ever forgive me for calling them Hansby tools? Yeah. So So what did I do? So, okay. So now you see that we got, see quite easily that we got ourselves a low-pass filter with a second-order transfer function. So the denominator is really something nice. And it should be the same as in the lecture notes. But now this is a signal flow graph. A signal flow graph permits me to calculate the transfer function from any node to any node. So I could also calculate it from V1 to V2. Let me do that here as a short notation. So I calculate it from here to here. Generate Mason. Here I copy it out. So now I don't go into the Python workbook again because we already know that the denominator is a nice second order denominator. But now you see that the numerator has become different. So before, the numerator did not contain the Laplace variable, so it was a low-pass filter. But from going to V1 to V2, now the numerator does contain one S, so we have a bandpass filter. And that is one of the nice things of this circuit, the Tau-Thomas biquad, that if you build this and then you go from here to here, from the input to this output here, V1 or Vout1 or Vout2, it doesn't matter. So these are both low-pass filters, but with a positive or negative sign. Then you have low-pass filter. But if you take this here as the output, which you can, because it is, after all, the output of an op-amp, it can drive something more, then you also have a bandpass filter. So with the same filter structure, you have two filter functions available with two different outputs. So at least from using op-amps and sacrificing a full op-amp to get the gain of -1, at least you win something. And so that's one of the advantages. And I would like to invite you to think about circuits and systems exactly like this. You will also get a new exercise where you have to think about how to analyze those circuits, also with non-idealities. And in order for you to do that, I have to introduce one more thing from the lecture notes, which you very much need. But before I do that, question, anything you want to know about the Tau-Thomas filter? Okay, so just digest it. Yes, please.
So this would be more a filter with discrete components, right?
The question is, I repeat it for the online users, yes, this will be more filter you need with discrete components, or could be. If it is also sometimes used on integrated circuits because there is a very big advantage to this kind of circuit, but it all has to do with second order effects. Here, all of the amplifier inputs are virtual grounds. So at the negative input of these amplifiers, there will be very little variation of voltage. Therefore, they will be very linear. So if you do it like this, you will get the linear filter, which can also give you a good linearity behavior. So not much distortion, if you already know what that is. If you don't, wait for lecture number 6. But here, in this filter, in these GM cells, the input does whatever it wants voltage-wise. So here, from these blocks, the voltage inputs, they jump. They really have the full signal swing. So it's hard to get this very linear. So it depends on what kind of filter you want in an integrated circuit. If this is a filter, for example, for the read channel of a hard disk or a DVD player or so, where linearity is not so important, but speed is, then the GMC filter definitely is your friend. If even if it is audio, you can tolerate quite a lot of distortion, if not disturbance, but distortion in audio. But if this is something where distortion is a problem, so very high linearity audio or so, then there is no way around doing something like this where you actually have very good feedback. So to keep the linearity low. But these are again second order effects, you see. So this only is worth thinking about what you do if linearity is an issue. On the PCB, if linearity is not an issue, but speed is, you can also build the first one because you can buy an integrated circuit which gives you transconductance. We will later see some of them here. I will introduce you the AD844 and the OPA860 with which you can do crazy and very fast things on the PCB. More questions? Yes, please?
One question. This feedback loop, why does it go to the V2 and not the V1?
The question is that why does the feedback loop here go to the V2 and not to the V1 in this schematic? The reason here is relatively simple. I hope I can also explain it in simple terms. The circuit you have here, and now it gets a little bit messy with the colors. So the whole circuit I have here with the G1 and this here. So this circuit. Now I erase that again, this blue blob. It is structurally exactly the same circuit I saw before, if I find it. That was below in the lecture notes. So this is exactly that, an op-amp with something in the feedback and one resistor coming from one node and the other resistor coming from the other node. And we have established with this analysis that this is what happens, that from one node you will have a transfer to the output and from the other node you will have a transfer to the output. It is not possible for an op-amp circuit that you have a transfer from this to the input, is it? But that's what you just asked for, essentially, when you said, why does it not go in the signal flow graph here? Oh no, I'm very sorry. I just saw that people online didn't see that, but I will not repeat. I hope you still understood it without seeing it. Oh, yes, you saw it because I was on the camera. So you maybe didn't see it very well, but that's what you asked for when you said, do you want to go from V4 to the input? Then you ask for what is the signal transfer from one input of the circuit where you have to the other input of the circuit. Yeah, but now it goes from input to output. Does this answer the question? Okay. Then let me do the final one, which I want to show you. So for this, I have to adapt the integrator loop filter, which I did before, to do the right thing. Yes? There is another question.
You mentioned about the advantages of using op-amp instead of transconductors for the linearity.
Yes, this.
So ideally, a transconductor with a buffer is basically an op-amp, right? So how does that actually change the whole scenario in terms of the
question was about op-amps and transconductors, and that the transconductor is basically the same as an op-amp. Here I could go very deep if I wanted. Actually, I want to go very deep there. So there is a full lecture here about that. I ask you to be patient. Is that okay? Thank you. But this will come. It is a very good question, so it deserves very much attention. So we will have a full lecture about how op-amps are built. Yeah. Okay, but let's go here. And I now want to adapt this here, this integrator loop, to the GMC filter. So I'll save as. I call this GMC filter. such that we don't lose it. I should make a break now, but I won't, because I think we have 5 more minutes and I would feel stupid in making a break and then 5 minutes and bye-bye. So bear with me. So the thing I wanted to do, and now I just type it off the, here I now just type it off the lecture notes. So the flow graph I wanted to have actually, this 1 over SC2 was okay, but in the feedback here, I wanted to call this GM3 here. And this here, I wanted to call, in the lecture notes, it's called GM1. This is on page 2 of 3 of the GMC integration. And that one, I wanted to be GM4. Okay. Now I move it a bit to a more pleasant. This is still one of the disadvantages of the tool. We don't know how to solve it. If anything is selected, then the cursor is where you can insert something, and therefore the Control A marks this as this text box and not the graph. But pressing Escape is just kind of good enough. So now I have this signal flow graph, and in order for you to make it better readable here, now that was a stupid idea because then you will not remember what it was. Anyway, my intention now is to also analyze noise sources in the circuit. So I want to know what noise is doing. And we will go into circuit noise a little bit later, more in depth. But in the lecture notes, I have already described the noise source of a transconductor. So these are 2 non-idealities I have in a transconductor. And one of the non-idealities you have in a transconductor is noise. I have to study my handnotes. Where is it? Because this here, what I found is the finite output resistance of the transconductors. Yes, it is much later. So here, this is noise of the noise model of a transconductor. And the way you very often see a noise model shown in textbooks is that they do it like this here. They say, okay, I have a transconductance element, and this transconductance element has input referred noise. So all noise is mathematically referred to the input, and we will, in a later lecture, I will show you what this mathematics means in formulas. But what it means is always that somebody goes and measures the noise that comes out of the device and then divides it by the transconductance and says, now input referred it is like this. However, this noise comes out of the device. It doesn't come out of the input of the device. It doesn't do that. Yeah. So it would be kind of, from my point of view, the noise model you see in all of the textbooks like this is stupid beyond compare. So what do you do here? You go and you put the noise source, a voltage source, somewhere in a circuit where it physically does not exist. That nothing good can come of that. Yeah? You will always be confused, because then it happens somewhere where it doesn't happen. So the only proper way, I believe, you have to treat such noise is to say, okay, it comes out of the circuit. Yeah? And so you could, if you wanted, just draw a second transconductor next to that and say, okay, this is this, and then it is added here, and here you just have the noise source. So this is what actually happens. physically if you do the source superposition. But we have a big advantage with the signal flow graph, don't we? So from the input referred noise voltage, if this is the signal path, we just can add another branch which goes to the same point as the GM with the same weight as the GM, yeah? And the input there is the input referred voltage. So if you have that, then you can now extend the input referred voltage of that circuit. Here I have a GM1, a GM2, a GM3, and a GM4. So that should be a little bit nicer. What did I do? Let's make it a little bit more compact. And now all of those here should have input noise sources. So the GM4 would have a VN4, voltage noise source of GM4. Then the GM1 would have a VN1, and the this is another GM1. That should be GM2. The GM2 here should have a VN2. And the GM3 should have a VN3. So now you have all of the noise voltage sources. And as I said, from each noise voltage source, you would have the same path with the same transconductance as you have for the transconductor itself. So I can now do that from every input here, if I do it right. This is the GM1. Then I would have from the VN2 to I2. I should have something where I have GM2. And then you have from the VM3 to the I2, I would have something with GM3. And now if you're not so satisfied with how it looks, you could tidy up a little bit here and make it a little bit nicer. It can help sometimes, but we are now not doing the documentation right now, but still doing the analysis. Yeah. So I see that I basically have two ways how the noise can go to the output. Yeah. Not four, only two, because VN1 and VN4 here, they are different inputs and they have different GMs going to the output, but they will have the same structure, just the component values will be different. So if I say, let's check what happens from the VN1 to the output, let me put it like this again, such that we can save the value. So if I want to go from VN1 to the output and calculate it, what happens, then the Mason gain I get, now something is hanging. Oh, I found another bug. Interesting. Okay. So I generate Mason and I get the transfer function. And it is not very surprising. I mean, we could have really omitted that step, couldn't we? Because it is the same as from the circuit input. So why did we bother? Yeah? It is just a low-pass filter, but not both noise sources will have exactly the same forward gain. One has the GM4 in it, like the main filter, and the other a GM1 instead of a GM4. It is a totally different question about going from VN2 to the output. VN2 and VN3, so if you go here from the input to the output, then I also calculate this transfer function, generate Mason. I copy it over to the to this here, such that you can see what Mason gave from VN2 to the output. And now you can see that we have a similar effect than we had in the Tau-Thomas filter. Here now suddenly I have an S in the numerator. So this is a bandpass filter. So fundamentally you see that the noise of two of the transconductors is low-pass filtered, and the noise of the other two transconductors is bandpass filtered. In case you have not yet heard in your studies what it means to have different noise transfer functions, then you need to remember one last thing. And of course, if you haven't heard it, you cannot remember. But if you have heard it and forgot it, you can remember. And this is the one last thing you need to know in order to solve the exercises. When I showed you how to combine signal transfer functions, I have to zoom out. If you compare the signal transfer functions, this we did down here, and then the correct solution for signal transfer functions is, of course, that you go, and if you have two signals at the input here, then you simply add the influence of both signals. This is what it means to be a linear circuit, isn't it? So input 1 times transfer function 1 plus input 2 times transfer function 2. It is not the same for noise, because with noise, decorrelated noise, the different noises of the sources of the transconductors, they are not correlated. And then you cannot add their amplitudes. You need to add their powers, noise power. And then, if you have different transfer functions from the input to the output, the correct way to do that is, for every noise source, you take the square of the absolute value, but the input referred noise is already given as an absolute value, not as a with phase and magnitude or so. So this is the square of the absolute value, and then you have to take the absolute value of the transfer function squared. And then you add all those squares. Yeah? And then you get the square of the output noise. And if you're not satisfied with having the square of it, then you have to take the square root later. Now I just have to find my position again. I pressed undo one time too many, so it jumped back on me. Here we go. Yeah. And really, it's quite funny to take a formula like this and evaluate it. Because sometimes, if you do that, you even find errors in datasheets of op-amps. So there is one example. I don't know whether I can find it again in a datasheet of analog devices, where they give you the budget of the total noise coming out of the circuit in a table, in table form, and the number is wrong. You can very easily test that now if you know this simple noise addition formula. Okay. From my point, this is it for today. So this is your last question possibility for today directly in the plenum. I will not immediately run away, but soon, but then you will still have the assistant. So has anybody here any questions left, either in the room or online? So then maybe we can finish that for today. We are not quite there with everything which I wanted to teach. you with filters, but it's enough for today. So next time I continue with the filters. I mean, it was nice to have one integrator loop filter already, but the Tau Thomas is not the only one. Another one is the one I can hardly pronounce. You can also not either, but I once had a Swedish person, his predecessor, Raphael's predecessor, Hampus, was from Sweden. And he told me the filter I'm going to introduce to you next time as the first filter is the Walker-Berry, a Mossberry filter. Americans would say Ackerberg-Mossberg or something like that, but then Hampus would always laugh and say, yeah, how you southern people cannot pronounce Swedish, it's funny. But this filter works a little bit differently, and that one is of course also possible to analyze with the signal flow graphs, but then we need another way of going at it, because today we looked at either using driving point signal flow graphs or using simplified signal flow graphs, and next time we will need to combine it. So part of the graph will be a driving point graph and the other part not. I'm looking forward to next week's lectures. I hope so are you. So I wish you a very good week and see you again here soon. Bye-bye.